Hello everyone. From today onwards, we'll be starting with a new video series that is Python programming will be performing for plotting different functions which might be used or may be used in communication engineering or which can be the functions which are being obtained after performing certain operations like modulation or demodulation etc. As you might be aware of that we can use different IDEs for Python coding like Spider we have PyCharm, Jupyter or basic Visual Studio we can use. But for this series I mostly prefer this Google environment, Google Colab environment. That is an online Google application which will be using for Python coding. It is just similar to the Jupyter notebook only. So we'll be starting our lecture series with the plotting of basic functions like unit step, unit impulse, ramp, exponential, etc. So to start with, I must first tell you from where I've opened this notebook. Actually, you can see a plus sign over here. We can simply click on here. You can access your Google Docs, Sheets, Slides, and likewise, if you click on more, you'll see a option for Google Collaboratory. If I click on that, the same notebook will appear, right? Or if it is not appearing, you can go and just add on this application to your Google account. All right. So let us start with renaming of the function. This notebook will name it basic functions. All right. And here there you can see the two options. One is for code, one is for text. We'll have to add text first. I'll click on this arrow so that this text will go on the top, and I'll double click. So to add the text content, I'll write to represent basic signal signals, we can say bracket signals in bracket we can write unit step, okay, unit impulse, ramp, comma, exponential, comma, sine we can plot, and cosine will be plotting. All right, and that too will plot using Python obviously. And this is our code part. Or if it is not appearing, then you can simply click on this code and it will appear in this notebook here, right? We'll start with importing a few important libraries which we'll be using here, like import matplotlib dot pyplot as plt, enter, import numpy as np, and we'll just click on this to run these commands. Obviously we'll be requiring these two libraries in here. Matplotlib is a very popular library for data visualization basically, right? All the plots or whatever we want to visualize, that will be enabled by this library only. Pyplot is a sub module of matplotlib. All right, and we'll be calling it as plt. Wherever we require this function to work, we'll simply write plt thing, okay. And second one is numpy. NumPy is again a very important library. It is for working with large multidimensional arrays or matrices. Okay, these arrays will be of numerical data obviously, and it provides a wide range of mathematical functions to operate like algebra, linear algebra, or statistical operations etc. And obviously for convenience we'll be calling it with np. Wherever we'll be requiring this numpy to work, we'll simply write np. Now next we'll again click on code. Just we'll separate two things and we'll start with our function part. So we'll write def unit underscore step, in brackets we'll write t, and we'll put this. Then it will return. We'll call this function np here dot heaviside, heaviside, in brackets we'll write t comma 1, will set the value default to 1. So in here we are actually defining a function unit step, and this heavy side actually is being called from this numpy library, as I just said earlier. So np is the short form for numpy. So heaviside is basically a function which takes on value 0 for t less than 0, and it takes on a value 1 for t greater than 0. Alright, it is just similar to whenever we have to plot this unit step. You know the basic properties of unit step. It is by default is equal to 1 for t greater than or equal to 0. Is it greater than or equal to 0? And for t less than 0, it is obviously equal to 0 only, right? The same thing the heaviside function returns. All right, it takes two arguments, you can say, t comma h, right? H we have defined by default, it is equal to 1, right? As it is a unit step function, right? Unit value it will be. Okay, t is the input value, or we can say the length of the function, and h is the height of the function, which is by default equal to 1. So let us run this thing and see what happens. So it is okay. I mean, no errors are there, right? So let's define a variable t equal to np. We'll again call that numpy function here. Np dot line space, in brackets we'll write -5. You can take any values of your choice. 100 bracket close, then enter. We'll define another variable y equal to, we'll write unit, we'll call that function which we have defined previously, unit step, and in bracket t. All right, and obviously we'll run this thing again. Sorry, it should be lin space. Okay, not line, line. So that was my fault. So as you can see, your line space is taking three arguments: -5, 5, and 100. 100 is the equally spaced samples, number of equally spaced samples. So this many samples will be having at the output, and the start point and the end point. So we can say that linspace is a function from NumPy library that returns an evenly spaced sequence, evenly spaced I'm saying, sequence of numbers, I mean 100 samples, evenly spaced from -5 to 5. Okay, now it's time to visualize this thing. So we'll call that matplotlib library as plt dot plot. In brackets it takes two arguments, t comma y, bracket close, enter. We'll write plt dot show, and in brackets sorry, we'll simply put the parenthesis and we'll run this thing. So as you can see, we have got the unit step function, right? Its maximum value is 1, you can notice here, and it will be 0 for all the values, for all the t values, values of t less than 0. All right, and for greater than 0 it is having a value 1, and it will range up to 5. So this plot ty will create a plot and show, actually this plt dot show is used to just visualize this thing. It displays the plot in here. So this was our unit step. Let's introduce some text here. We'll again click on this arrow to move it above this thing. We'll write unit step. All right. So we'll have to introduce this text again, right? We'll be mentioning what we are performing. Suppose we are performing unit ramp, we'll write unit ramp here, and thereafter we'll introduce this code thing, and we'll start with the definition part directly, as the libraries are already being called, so no need to call them again. So we'll write def, what function we are calling, ramp. So we'll write ramp in brackets t, and we'll put these symbols here, enter. Return from np library, we are calling this function where, in brackets we'll write t greater than equal to 0 comma t comma 0, and we'll close the bracket and just run this thing. As you might be knowing the basics, the ramp function is nothing but it returns a value equal to t. T is this thing, this axis here, right? So it should return a value t. If t is 1, then this thing here must be equal to 1, right? If t is 2, it will return a value 2. So that way we have defined this logic here. T is greater than equal to 0. So for that there are two arguments, t comma 0, right? If t is greater than equal to 0, it will return a value t, right? As you can see in here. And if it is less than this thing, it will obviously return a value 0, right? Either it returns t or it returns 0. Now we'll introduce this code again, and obviously we'll copy this thing from here only. Actually that is quite similar to that above function. So we'll copy this thing here, and in place of unit step we'll write this thing as ramp. We're calling this ramp function only. Okay, so be careful about that. We'll run this thing and introduce one more code, and we'll call this thing here, these plot things. Okay, so that we can visualize our plot. Okay, so as you can see, we can just identify that when t is greater than 0, the function is equal to t only, right? Otherwise it is returning a value 0 for t less than 0. Okay, that is our ramp function. So let's say our next function is exponential function. So we have to introduce this text again. I will write exponential. Okay, and thereafter we'll introduce the code. Again we'll start with the definition part. So let's define exponential. In brackets we'll write obviously t and enter. Well, it should return np dot exp is the default function which is already being defined in numpy library, right? Minus of t, suppose for instance we are taking this as minus of t. We'll run this thing again. We'll introduce this code, and we'll copy the same thing from above code, paste. Again we'll introduce this thing, and we'll copy it from this code here, right? Control V, and obviously we have to change this function to exponential. All right, so let's run this thing. You can see this is a decaying exponential, as we have mentioned this thing, this minus sign we have mentioned in front of t. If we remove this minus sign, you'll see the changes. Okay, it is now a growing exponential. Okay, increasing towards this side. All right, so that is how we plot the exponential functions. So our next plot will be unit impulse. First introduce the text in similar way. We'll write unit impulse, and thereafter we'll introduce the code part. Okay, we have already defined the we have already called the libraries, right, by import command. So we'll start with the definition part, defining the function. We'll write def unit underscore impulse. In bracket we'll write t, the same way we were doing for other functions. Then return np dot, the same thing, same function will be calling from that numpy library, where sorry, by mistake I just pressed the enter button. Okay, where bracket start t is equal to 0 comma 1 comma 0. Again it's a conditional thing. So whenever your t is 0, it will return a value 1, otherwise it will be 0 throughout. Okay, so we can run this thing, I think. All right, so I'll introduce another code here. Okay, so we can simply copy this thing from above code, control V, and in place of exponential we'll have to write unit. I think I've mentioned something wrong. unit, unit impulse it should be, right? So that function I'm calling in here, right? Thereafter introduce one more code here, and we'll start to plot this thing. Plt dot plot t comma y, right? Enter plt dot stem and plot are quite similar, but in plot we will see a continuous thing, but in stem we'll see discrete values like samples. Okay, just like we do in MATLAB. Okay, so 0 1. Okay, so and if we want to just color this thing, we can mention some color here, red, comma, and what type of graph you want it to be, so you can just put that thing here, right? So this will plot value 1 at 0 t equal to 0. Okay, then we'll define some limits, just like we do in MATLAB. We define some axis values. Okay, so similar way we'll write plt dot, sorry, x limit will suppose mention it from -5 comma 5. Okay, we'll close the parenthesis, then enter. We'll have to mention some x limit values dot y limit values. Sorry, x limit we have already defined, so let's say it is ranging from minus 0.2 to, let's say it is going up to 1.2, and enter. Then plt dot show, and again close the brackets. We'll run this thing again. Oh, we haven't got this plot. Why? All right, I have by mistake written here step instead of stem. It should be stem, right? So I think now we got this thing, right? That is your unit impulse function. Okay, so next we'll be plotting sine and cosine functions. So let's start with sine, introduce the code part. Firstly, again we have to define this function def sine in brackets t, obviously, enter. It should return something. It should return, actually there's a predefined function in your NumPy library. It is sine brackets t, right? So let's run this, and in the meantime we should introduce one more code. We'll have to write t equals np dot, same thing, lin space from -5 to 5, and 100 equally spaced samples we'll consider. Okay, enter. Y equals sine t, the function we are calling here, right? Let's run this and introduce one more code here. So plt dot plot will plot between t comma y. All right, and to display this thing we'll write plt dot show parenthesis, right? So you can notice here's our sine function, and in similar way we can generate the cosine thing. Okay, the only thing we'll be doing is we'll change the function we are calling from NumPy library. Okay, cosine. So let's introduce the code. We'll define this thing, define cosine bracket t, right? Return, it should return this cos function, sorry, np dot cos function. It is actually from np library, NumPy library, cos brackets t. Okay, let's run this thing. Yeah, we are going good. Introduce one more code. So t equals np dot lin space, it will range from -5 to 5, and 100 samples you can consider 1000, there is no issue. Okay, more the number of samples, more will be the accuracy. Okay, more smooth your curve will be. Y equals cosine, I'm calling that function from above. Okay, bracket close. Let's run this thing and we'll introduce one more code here. Plt dot plot t comma y, and to display this thing we'll write plt dot show parenthesis, so you can notice the difference. All right, so that's your cosine function, you'll notice in here. If I replace this plot with stem, so it will look like samples. You can just get it more clear by reducing the sample rate. All right, so this way you can either plot uh, the continuous value, or you can just have the discrete value of this thing. Okay, so in today's video we have discussed different elementary functions like unit step, unit impulse, ramp, exponential, and some continuous time functions like sine and cosine functions. Okay, so this is all for now. We'll continue our discussion in upcoming lectures. For now, thank you and have a nice day.